everyone, how are you all doing? I hope everyone is doing good and great. I'm Mahesh, your physics teacher, and you're watching me on SMR Online Physics. Today in this class I'm going to discuss about refraction of light by spherical lenses, the lens maker's equation and the thin lens formula. Are you ready for that? Yeah! So now we are going to discuss about refraction by spherical lenses. In the last class I discussed about refraction by a spherical surface, and we got a beautiful relation, a very important relation relating the refractive indices of both the mediums, the denser, the rarer medium, the image distance, the object distance and the radius of curvature of the spherical surface. That equation we are going to use to derive the lens maker's equation. A very important fundamental relation relating the curvature of the surfaces as well as the image distances, the object distances and the refractive indices of the medium concerned. Alright, we will have a great time, my dear. Let's continue. But if you haven't watched my previous class, do watch it, get the concept clear and then come back to this. Then you'll really enjoy this class. Great, come on. So refraction by a spherical lens. Now I will show you a beautiful diagram and it will be a slightly odd kind of a shape indicating a very thick fatty lens. Alright? Something like this. Just follow me. This is one surface and other is somewhere there. This is the other, yes, the other curvature having a different radius of curvature, and let us assume that we are deriving it for a really fatty lens of thickness L. That's good. Now observe it very carefully, okay? It's beautiful physics here. So a ray of light which is incident at right angles to the curvature goes undeviated right through both the surfaces. That's it. That's it. Point 1. Just goes through it. Alright. Now let us assume there is an object, a point object close by to this spherical surface 1. And let me just draw it over here. Let us say this is the point object O. Please listen carefully. Right? So a ray of light from this point object going perpendicular to the surface goes undeviated through it because it is the direction of the normal. We call it as normal incidence. Now let a ray of light emanating from this object strike the spherical surface 1 at a given point, making a certain angle with this principal axis. Let us call it as alpha. So at this point, as I discussed, the normal is always a perpendicular line which is drawn to the tangent of the surface and is always connected to the center of curvature. Let us call the center of curvature as C1 for the surface number 1. Okay, hope my drawing is correct and good. Perfect. Okay, all good. So this becomes your angle of incidence. The ray of light is going from one medium to another. So let us mark the refractive index of this air medium as N1 and the other medium of glass, that is N2. So naturally N2 is greater than N1. Alright? So here we go. So it doesn't go straight, it rather curves towards the normal, and let us say it curves some bit like that. So this is your angle of refraction. Alright? So now what will this ray mean for this surface like? This ray is the refracted ray from the first surface. So this ray of light, when produced backwards, meets at some other point. I'm trying to get it straight. Yeah, that's look good. This is somewhere here. So this is where a virtual image of this object is formed because of the first refraction, a single refraction happening at the first surface. So let us give the names here. This is your radius of curvature. Let us call it as R1. This is your object distance U, and this is the virtual image distance, which is not the real image at all. It's an image which is formed only by the first refraction happening at the first spherical surface. Then I will move forward. So for this first phase, let us call this first phase AB. For the spherical surface, AB, come on, let's enjoy and do it. That will be more fun. You need the equation which I taught you in the last class. So this is N2. So N2 by the image distance. This is very much a temporary image distance. This is a virtual image formed. Plus the refractive index N1 of this rarer medium by the object distance. U is equals to N2 minus N1 by R1. That's good. But this is an equation which is written plainly without any sign convention. So let us use the sign conventions, which is very similar to the spherical mirrors. So N2 by V prime. Even if you put V prime as negative, ultimately it's going to turn positive because we are deriving it for a real image which is about to form on the other side of the thickness of this lens. So it will be N2 by V prime. And you can see that is to the left of the spherical surface, to the left of the main optical center of this spherical lens. So I can easily say it should be N1 by U, the minus sign coming because of the negative distance, R1 to the right hand side, so no harms to the right. So this is N2 minus N1 by R1. Let us call this as equation 1, done for the spherical surface AB. Great. Happening at the second refracting surface, the second spherical surface CD, which has a different radius of curvature. Now the ray of light which is passing right through the thickness of this lens. If you imagine someone sitting at this point and looking at this incoming ray, for that person, if it doesn't realize there is a curvature out here, for this person, listen to me carefully, for this person, this ray would have been almost looking like, seems to be coming directly from I prime. That's the trick in this derivation. Be very careful, be very focused. For this particular imaginary person, this I prime, the virtual image from the first refraction, will be behaving like a virtual object. Something new it sounds. This virtual object for this refracting surface will be the cause for the formation of the actual real image. So just imagine the situation like this ray of light is coming completely from a medium of refractive index N2, and now you can draw your normal very carefully. You will see that, yes, pretty good. This is your curvature C2. Possibly we have taken that this is different from R1, so this is, let us say, R2. So this will be your angle of incidence. The ray of light is going from denser to rarer medium, so it will be bending down. So the intersection of these two rays at a given point always gives rise to the formation of a real image. So this is, my dear, the actual image distance V, a formation of a real image by this lens. So let us write an equation for this surface CD. So for the spherical surface CD, this surface, how would the equation look like? N2 by this entire object distance. The entire object distance for this surface, my dear, I hope I'm very clear to you. This is like V prime plus L, because this point feels that as if the entire thing has come from a medium of N2. So N2 is on the left hand side, so minus V prime plus L because of the sign convention, plus here we have N1 this refractive index being exactly the same as the first medium, so not to complicate the matters, let us take it as N1. So if I have N1 here and it's on the right hand side, N1 by V, that's the case, is equals to N2 being a greater value, N2 minus N1 by, what would be the sign convention for R2? To the left of the optical center, so it should be minus R2. That's it. Just quickly rearrange the equations. Let us write this way, N1 by V minus N2 by V prime plus L, and this is like, say, minus is taken common there, the N1 minus N2 by R2. Hope I'm connecting right to you. Very good? Great. So here I put a special condition. Now this is the consideration, that's it. Very good for this entire thing. But suppose if you do it for a very thin spherical lens, if the lens is really thin enough so that this capital L can be taken negligible absolutely, if, I write if here, if L equals 0, then the equation would have read as N1 by V minus N2 by V prime equals N1 minus N2 by R2. So this would be our equation number 2. Clear? Now let's add up the equation 1 and 2 and to get our final result. So I need to rub this for some space. This is my equation 1. I want to get rid of this part. And let us quickly do it. Yeah. So adding 1 with equation 2, we should be getting like N2 by V prime minus N1 by U should be equal to N2 minus N1. Sorry, I need to add the equation 2. Yes. Plus N1 by V minus N2 by V prime should be equal to N2 minus N1 by R1. This is plus N1 minus N2 by R2. That's it. Simple. So if you observe here, now I don't need these equations, get rid of it. Yeah. Now you see that N2 by V prime, N2 by V prime get cancelled off. Plus and minus, let us rearrange it beautifully. N1 by V minus N1 by U is equal to, I take a common there, you can see here, N2 minus N1, N1 minus N2, take the minus common out there. So you'll end up getting N2 minus N1 out of the brackets, and inside you'll be left with 1 by R1 minus 1 by R2. So even if you can see here, N1 is common again on the left hand side. So if I take it on the right hand side directly, it looks like 1 by V minus 1 by U is equals N2 by N1 minus N1 by N1 into 1 by R1 minus 1 by R2. Not a big deal. Perfect. That is also a very good equation. Now I think finally I can get rid of that diagram. We need some space. Yes, yes, yes. Right. I don't want to go low half there. So this is pretty good now. If I put a condition, if the object distance, the object would have been extremely far, like at, we say, object at infinity, then we know that the image distance would be exactly equal to the focal length of the lens, that is f. So we should find in this equation coming up is 1 by f and 1 by infinity taken as 0, and you can see over here we'll end up getting n to 1 minus 1 into 1 by r1 minus 1 by r2. My dear, this is called lens maker's equation. This is your lens maker's equation. Hope you got it. Equation 1 by v minus 1 by u is equal to this and this. You'll find that the right hand sides are exactly the same. So hence on comparison I also get a relation 1 by v minus 1 by u equals 1 by f. This is called as a thin lens formula. I will definitely show you. Do not go away from my class. That is the formula if you wanted. But if you want to see another variant of deriving this formula, which is more applicable for school kids 9th and 10th, stay tuned. Now let me discuss about the thin lens formula, right? Okay. Now I'm going to show you how to derive the thin lens formula, which is well known to all the students. Just now we saw it, but I will do it from concave lens, very rarely done in classes. The formula will look something like this: 1 by image distance minus 1 by object distance is equal to 1 by the focal length. Along with this, we will also derive the magnification for the lenses. Alright, so let me draw a beautiful diagram. This space is perfect for that. So let me draw a concave lens, which is by nature a diverging lens right now. So we have this right, the principal axis passing right through the optical center. A lens will have double curvatures, as we all know now. Let us call this as first principal focus. The center of curvature also termed as 2f1. And then we have the second curvature, second focus. And this is your second center of curvature, 2f2. So if I place the object anywhere in between the infinity and the optical center, we'll always find the same kind of an image. So let us term the object as xy, xy referring to the size of the object. So a ray of light emitted from the object parallel to the principal axis always seems to diverge away from a virtual point on the principal axis that is called as the focus. So this is how it looks like. Alright? Now next, any ray of light passing right through the optical center seems to go undeviated. That's it. So thus a virtual image, an erect image, but a diminished image is formed. So this tip represents x dash and y dash, representing the size of the image. Using this simple ray diagram of concave lens, let me show you how to get to the thin lens formula, right? To observe this diagram carefully, the angle made by this ray of light, let us call this as theta. So these two tiny triangles, as you can see that, this is x prime, y prime, O, and x, y, O are very, very similar triangles. So from triangles x prime, y prime, O, and the triangle x, y, O, we can write, what we can write, my dear? We can write easily what is tan theta equal like. So tan theta should be equal to x prime by y prime by O y prime, and that should be equal to xy by O y. Alright? Because you understand, because these two triangles, similar triangles, the ratio of the perpendicular by the base is your tangent of the theta. So now putting in the values, this x prime, y prime is your height of the image. It is placed above the principal axis. So the sign is positive, plus h prime. Then we have oy prime, which is to the left of the optical center. That is your image distance. So minus v. That is equal to xy, the height of the object. Please note it's still above the principal axis, so this is your plus. And oy, O to y, this is your object distance to the left of the optical center. So minus u, small rearrangement will give us the equation h dash by h is equals to v by u. This terminology represents small m, m standing for magnification achieved by thin spherical lenses. Right? Now from here onwards we'll move to the lens formula. Now similarly, we'll also find two more triangles hidden up there. So let us connect these points. Let us call this point as M. This is like a bisector of the entire thin lens vertically. Now if you observe it very closely, we still have the angle created by this divergent ray. Let us take this angle as alpha, and still we get this tiny triangle with the angle right angle, and this is another right angle. So again we have from the triangles x prime y prime f1 and the triangle MO f1, we have the tangent of alpha being exactly equal to each other. So you can write x prime y prime by y prime f1 should be equal to MO by OF1. So if you observe this equation carefully, we know what is this x prime y prime is. This is nothing but your height of the image, so plus h dash. But y prime f1 doesn't have a unique name, so I can write it like OF1 minus OF1 minus OY prime. That's equal to MO. MO is parallel to this XY, so that distance should represent the height of the object above the principal axis, so positive sign OF1, O to F1. This is your focal length to the left hand side of the optical center. Remember, for concave lenses the focal length is always negative, so minus F. So putting in the values quickly, yeah, it's pretty hot out here, plus H dash. Okay, OF1, this is your focal length of minus F. This is OY dash, that's your image distance left side. So again you get a minus, so this is minus of minus V, and hence you get minus of H by F. That's it. So you can easily see that. We could have done it many ways. H dash by H, this comes down. You have this minus there, this is F over here, this is V minus F put in there. Alright, so just now we derived what is H dash by H is equal to, just put in the place there, that is equal to V by U, and take care of this minus, okay, should not cause any trouble. So I can write it as F minus V by F, or VF is equals to UF minus UV. Now you exactly know, because you have seen it already for spherical mirrors, that divide all the terms with UVF. So VF divided by UVF, UF by UVF, minus UV divided by UVF, and you get a lot of terms getting cancelled out. UF is out, UV is out. Hence, what you are left out, should I show you out there? Absolutely yes. This is 1 by U equals 1 by V minus 1 by F. Just small rearrangement, 1 by V minus 1 by U equals 1 by F. The kids watching this class should definitely enjoy how easy it is to get to the lens maker's equations and the thin lens formula applicable for lenses. See you again in my next class on SMR Online Physics. Do not forget to log in back. Have a great time ahead. Bye-bye.